A compact claim to test right away. At the same aperture and pixel count, a physically larger sensor usually captures more usable light, wider dynamic range, and cleaner shadows. And that difference shows up in raw samples, teardown photos, and vendor datasheets. We'll follow that testable idea into 5 concrete sensor formats, show where pixel size, lens aperture, and stabilization matter, and explain when clever computational processing actually narrows the gap. Receipts live in Sony and Samsung sensor datasheets, DxOMark lab comparisons, optical formulas for diffraction and entrance pupil, teardown module photos, and side-by-side raw comparisons. Chapter 1. 1.55 inch. This is the size most smartphone makers used for several years, and the setup claim we test is the classic marketing line, same megapixels, different performance. The receipt comes from numerous teardown photos and sensor spec sheets that list active pixel size and total area. They show 1.55 sensors with pixel pitches in the 0.7 to 0.9 micron range. Mechanically, smaller sensors force smaller pixels or more aggressive binning to hit megapixel targets, which raises read noise and reduces well capacity, limiting dynamic range under the sensor's specified ISO behavior. Optically, these modules need very short focal lengths to hit field of view targets, and that shrinks the entrance pupil unless you give them a physically larger lens stack. The takeaway? 1.55-inch designs penalize shadow detail and high ISO headroom at the pixel level, but they're cheap, thin, and benefit most from computational multi-frame stacking. That sets up the next size, where pixels start to grow. Chapter 2, 1.13 inch. The claim here is that modestly larger sensors offer a big jump in low light stringency for a small size cost. Receipts include sensor datasheets showing pixel pitches around 1.0 to 1.4 micron and DxOMark tests that consistently rank 1.13-inch modules above 1.25 in noise and dynamic range. Mechanically, the extra sensor area increases per pixel photon collection by the ratio of areas, lowering required gain and preserving mid-tone detail. Lens design relaxes slightly too. A longer focal length for the same field of view gives a larger entrance pupil at the same f number, which improves depth of field control and bokeh. The takeaway? 1.13-inch balances compactness and performance, and it's often the sweet spot where optical constraints and sensor physics align. That makes the 1.112-inch leap more interesting. Chapter 3, 1.112-inch. The setup is just a small jump in inches, a big jump in capability. Receipts include manufacturer spec pages and raw comparisons showing noticeable SNR improvements and cleaner highlights versus the 1.13-inch class. Mechanically, this size often allows pixel pitches around 1.4 to 1.6 microns at common megapixel counts, doubling well capacity versus smaller classes and improving dynamic range by measurable dB on lab charts. The larger pixels also make OIS, optical image stabilization, more effective, because each stabilized motion translates to more photons per sampling window. However, diffraction limits begin to appear earlier as you stop down. The optical formula for diffraction-limited spot size shows smaller apertures hitting resolution ceilings sooner on a denser sensor. The takeaway? 1 from 1.12 inch gives a real measurable boost for night shots and highlight retention, and it plays especially well with OIS and larger apertures, which primes the viewer for the transition to true 1-inch class sensors. Chapter 4, 1 inch. The claim is blunt. A 1-inch sensor behaves more like a compact camera than a phone sensor. Receipts come from compact camera teardown images, lens specification sheets, and DxOMark comparisons that show larger dynamic range and better high ISO performance for 1-inch sensors versus smaller mobile modules. Mechanically, the area jump increases both photon budget and depth of field control. At the same aperture, a 1-inch sensor accepts many more photons, lowering ISO needs and reducing noise. The entrance pupil and focal length required match better with physically larger lens elements, which reduces aberrations and improves edge-to-edge sharpness. On the flip side, you face thicker modules and heavier optics, and diffraction becomes a practical limit at smaller apertures for high-resolution variants. The takeaway: 1-inch sensors are the point where lens quality and sensor area both visibly improve images, making them a strong fit for hybrid shooters who want significantly better image quality without full mirrorless size and cost. Chapter 5: APS-C. The setup tests the crop sensor is nearly full frame idea for everyday photography. Receipts include manufacturer data sheets and mirrorless camera lab measurements showing APS-C sensors with much larger pixel wells and lower read noise than any mobile class. Mechanically, APS-C adds a large area advantage. For the same pixel size, it multiplies total light collection and dramatically improves dynamic range and bokeh control. Lenses scale differently too. An APS-C sensor uses longer focal lengths for equivalent framing, which changes the optical design and frees designers to use larger, sharper elements. But the trade-offs include weight, cost, and system depth. Lenses and bodies scale up quickly. The takeaway: APS-C behaves like a true camera system step-up. More control, higher image quality, and a lens ecosystem that matters for long-term flexibility. Mid-synthesis. Sensor area rule. Across these chapters, the pattern is clear and repeatable. Physical sensor area drives 3 linked mechanics: photon budget, per pixel well depth, and angular acceptance of optics. And those mechanics govern noise, dynamic range, and depth of field behavior. Supplier specs, teardowns, and DxOMark lab numbers consistently reflect this area-driven pattern more than nominal megapixel counts. In practical terms, larger area usually wins for raw image quality when optics and stabilization scale appropriately. Counterexample: computational narrowing. That rule has a powerful counterweight: modern computational photography. Receipts from raw sample comparisons and vendor white papers show small sensors using multi-frame stacking, smart demosaicing, and aggressive noise models to approach larger sensor results in JPEG output, especially for static scenes or night modes. Mechanics. Pixel binning effectively increases apparent pixel size by combining neighboring pixels, while motion estimation and alignment let multiple frames add signal without proportional noise. But the caveat is measurable. Computational fixes rely on scene stability, controlled motion, and headroom in highlight detail. They can't invent per-pixel well depth or eliminate diffraction physics, and forensic raw comparisons show the limits. The takeaway: software narrows gaps for many everyday shots, but physics still rules in challenging lighting, high dynamic range scenes, or where optical characteristics matter. Rotating cases, OIS, aperture, and lens quality. 3 rotating variables change how sensor size feels in real life. First, OIS multiplies photon collection for longer exposures. Teardowns and stabilization patents show larger sensors paired with multi-axis OIS gain more from slower shutter lines. Second, aperture interacts with diffraction. Optical formulas and lab charts show smaller pixels lose sharpness at smaller f-stops sooner than larger pixels. Third, lens quality and entrance pupil size matter. Even a large sensor underperforms with a cheap, tiny lens element. The takeaway: sensor area must be considered alongside stabilization, chosen aperture, and lens construction. Practical buyer ladder: mobile, hybrid, mirrorless. For phones, the rule is clear: prioritize larger sensor area in the main camera and effective OIS over chasing raw megapixel counts. Receipts are DxOMark and teardown data, where phones with larger main sensors and OIS outscore high megapixel competitors. For hybrid compact shooters, 1-inch sensors offer the most bang for pocketable size and good optical system support. For serious image control, APS-C gets you lens selection, ISO headroom, and depth of field control that mobile compute can't fully emulate. The takeaway? Match your use case, fast candid shots, low light scenes, or shallow depth portraiture, to the sensor class and expect diminishing returns from pixel counts alone. Final synthesis, a simple rule of thumb and next step. If you want one portable rule, use this. Give preference to sensor area and effective pixel pitch first, lens aperture and stabilization second, and megapixel headline last. Sensor area predicts per pixel photon capture and dynamic range. Aperture and OIS translate that area into usable images. Computational tricks are the tail that wags the dog in controlled scenes, but don't overturn physics in edge cases. If you enjoyed this breakdown, the natural next video is a practical optics primer, showing how focal length, entrance pupil, and lens aberrations interact with these sensor classes, and how to read lens spec cards the same way we read sensor data sheets.